Good morning, good afternoon, and good evening to everyone who joins us from around the world. We're so glad you're here.
Absolutely. It's great to be here.
This is Andrea and Renee. Welcome to the Stack series.
Always a pleasure.
Today, we are exploring the concept of reality compression.
And this is a really big one.
It is. I want to start by throwing out a thought experiment for everyone listening, something that has been honestly keeping me up at night since I started digging into the source material for this.
I think I know exactly which analogy you're going to pull out.
Right. So I want you to imagine you are standing in the Louvre. You are looking right at the Mona Lisa.
No glass in the way, just right up close.
Exactly. You're seeing the tiny cracks in the oil paint, the really subtle gradients of the smile, the dust motes floating in the air of the museum.
Just a massive amount of sensory input.
Right. It's a completely high-fidelity experience. Millions of bits of visual data are just flooding your retina every single second.
Total sensory saturation.
Yeah. Now imagine you step back and you snap a quick photo of it on your phone and you text that photo to a friend.
Okay.
You have just taken that massive, unfathomable flood of photons and you crushed it. You ran it through a JPEG compression algorithm on your phone. You stripped away probably 99% of the actual raw data. The file size is tiny now.
But when your friend opens that text on their phone...
They still see the Mona Lisa.
Right. You don't just see a random mess of colored pixels.
Exactly. They see the smile, they see the essence of the painting, because the compression algorithm basically decided what was signal and what was just noise.
It threw away the noise and it preserved the semantic meaning.
Which is a brilliant metaphor for what we're getting into today.
Yeah.
Because you sacrificed all that fidelity for efficiency, but you kept the truth of the image.
It's the core of the discussion.
But here is the terrifying part, and this is really the crux of our whole exploration today. What if that isn't just a trick our smartphones do? What if that is what we are? What if our biological brains, our whole evolutionary history, and maybe even the fundamental laws of physics themselves?
What if they're all just compression algorithms?
Exactly. We are effectively asking if the reality you perceive every day, the chair you're sitting in right now, the sound of my voice, is just the compressed JPEG.
And the actual real universe, the base reality, is this unthinkably high-dimensional raw file that we just physically cannot access.
We're going to take this concept of compression and we are going to trace it all the way from the foundational math of data science right through the biology of how we perceive the world.
And then we're going to land squarely in the weirdest, most mind-bending corners of theoretical physics.
We are talking about black holes, the holographic principle, and this incredibly provocative idea that space-time itself is really just a user interface.
Which I know sounds like pure philosophy or science fiction, but as we go through the sources today, you are going to see it is grounded in very hard math and thermodynamics.
So let's just get right into it.
Let's do it.
We need to start with the foundations. Section 1 here is what we think we know. And to do that, we have to talk about data.
But not just rows and columns in a spreadsheet.
Right, not just volume, but the actual geometry of information.
Because when people talk about big data, they usually just think of a lot of files. But the real challenge is complexity.
The sources refer to this concept, and I love the name of this. It sounds like an old Lovecraftian horror story. The curse of dimensionality.
It really is a curse if you're a data scientist.
Now, normally when we hear the word dimension, we think length with height. Maybe time is the fourth. But in data science, that's not what dimension means at all, is it?
No, not in this context. In data, a dimension is simply a feature. It's a single variable.
Okay, so give me an example.
Sure. So if we are looking at a medical data set of patients, one dimension might be the patient's age.
Got it.
Another dimension is their resting heart rate. Another is their blood pressure.
So if you have a high-resolution image, say a single photograph with 1 million pixels, and every single pixel can change color,
then mathematically you are working in a 1 million dimensional space.
That is so hard to picture.
It's impossible to picture. But mathematically, every single possible image you could ever take is just one specific point sitting inside that million-dimensional hypercube.
And this is exactly where the curse kicks in. Because our brains are completely hardwired for normal 3D space.
Right. We intuitively understand how distance works in 3 dimensions.
Like if I drop a needle in a haystack, it's obviously hard to find, but I intuitively know it's close to some pieces of straw and it's far away from others.
Precisely. You have a concept of proximity. But as you start adding more and more dimensions, the whole geometry of the space just breaks down entirely.
Explain how it breaks down.
Well, the actual volume of the mathematical space expands exponentially. So if you construct a hypercube with, say, 100 dimensions, the corners of that cube are so vast compared to the center that almost all of the internal volume is pushed out into the corners.
And that totally messes with the whole concept of measuring distance, right? I remember reading about this in the stack and high-dimensional space. Everything basically becomes equidistant from everything else.
Yeah, it's wildly counterintuitive. But if you randomly pick a point in a 10,000 dimensional space, the mathematical distance to its absolute nearest neighbor and the distance to its farthest neighbor are essentially the same.
Which means the whole contrast between what is close and what is far just completely evaporates.
It vanishes.
Which has to be a total disaster if you were trying to do any kind of actual science or machine learning.
It's a nightmare. Because if you can't tell what data point is similar to another data point, you can't classify anything.
You can't say, oh, this patient's profile is very similar to that patient's profile, so let's use the same treatment.
Or this current stock market trend closely resembles the crash of 2008. If distance is meaningless, it's all just uniform static.
So to actually make sense of the real world, we have to cheat.
Exactly. We have to make a huge assumption. We have to assume that the real-world data doesn't actually fill up that entire massive million-dimensional space.
And this brings us to what the sources call the manifold hypothesis.
Right. The core idea here is that while your data technically exists inside this giant high-dimensional space, the actual meaningful information, the signal, lies on a much lower dimensional shape.
A manifold.
Yes, a manifold that is twisted and embedded inside that larger empty space.
The classic example they use in the literature to explain this is the Swiss roll.
It's a great visual. Imagine a flat two-dimensional sheet of paper. That's a simple low-dimensional surface.
Okay, I'm picturing it.
Now take a pen and draw a pattern on it, a bunch of dots. Then take that piece of paper, roll it up tight into a spiral shape like a Swiss roll cake, and suspend it inside a 3D glass box.
Right, so now it's existing in 3D space.
Exactly. If you look at it strictly in 3D point A, and point B might look physically very close to each other, simply because the layers of the rolled-up paper happen to be touching.
But if you were a tiny ant walking along the surface of the paper, those 2 points are actually really far apart.
Because the ant has to walk all the way around the spiral. The true underlying distance is along the unrolled sheet, not the artificial shortcut through the 3D air.
And the older traditional linear algorithms, things like principal component analysis or PCA, they are notoriously bad at handling this right.
PCA is a blunt instrument. It basically tries to squash that Swiss roll entirely flat, like a pancake.
Like shining a flashlight and just looking at the 2D shadow it casts on the wall.
Right, and in doing that, it completely destroys the spiral structure. It permanently merges data points that absolutely shouldn't be merged.
So to fix this, we need what the sources call nonlinear dimensionality reduction. We need algorithms that know how to carefully unroll the paper.
That's where we get to modern tools like TSNE, which is T-distributed stochastic neighbor embedding, or UMP.
How do those differ from PCA?
They don't care about the overall global shape of the data right off the bat. They hyper-focus on local neighbors.
So they look at a point and say, who is standing right next to you?
Yes. The algorithm essentially says, I'm going to make sure this specific data point stays very close to its 3 best friends, and honestly, I don't care where the rest of the data set ends up.
And by strictly preserving those tiny local friend groups, those micro relationships, it somehow manages to organically unfold these incredibly complex knots.
It untangles a high-dimensional hairball into a flat, neat 2D map that human eyes can actually comprehend.
I've actually seen some of those UMP visualizations used in single-cell genomics. It's wild. You take a data set measuring 20,000 individual genes.
Which is 20,000 dimensions.
And you run it through UMP, and it just gracefully turns into these beautiful, distinct little islands of specific cell types on your screen.
It really does feel like magic when you see it work.
It feels like magic, but it is pure topology. It is an algorithm discovering the hidden, latent structure of reality.
Which leads us perfectly into the piece of technology that I really think is the main protagonist of this first section.
The autoencoder.
The autoencoder. It is such a fascinating piece of engineering because it is fundamentally a neural network that is deliberately designed to fail.
Designed to fail. Explain that, because usually when we talk about AI and neural networks, we want them to succeed flawlessly.
Well, an autoencoder has an incredibly simple job on paper. Its only goal is to copy its input directly to its output.
Okay, so if I feed it a digital picture of the number 2, it should just output that exact same picture of the number 2.
Exactly.
But that sounds completely trivial. I mean, a standard office photocopier can do that.
It would be entirely trivial if we didn't intentionally handicap the network.
Ah, the bottleneck.
Right. The architecture of the network is shaped exactly like an hourglass.
Okay.
The input layer where the data enters is huge. The output layer where the data exits is also huge. But the middle layer, the waist of the hourglass, is extremely tiny.
So it's basically like trying to force a full-grown elephant through a keyhole and then desperately trying to reassemble that exact elephant on the other side.
That is a very vivid image. But
Yeah.
yes, mathematically that is what is happening. The network is forced to take this massive, high-dimensional input, compress it down into a tiny latent code in that bottleneck, and then the decoder side has to rebuild the original data using only that tiny code.
And because that bottleneck layer is so restrictive, it physically can't just memorize the raw pixels, right? There just isn't enough memory to say pixel 1 is white, pixel 2 is gray.
There's nowhere near enough room to write all that down.
So what does it do instead?
It is entirely forced to learn the underlying rules that generated the data in the first place.
Oh, wow.
It has to learn abstract concepts like this is a closed loop, this is a diagonal curve, this is what the structure of a handwritten digit looks like.
So it learns the parameters of the data instead of just parroting the data itself.
Precisely. And the magical side effect of this is that it actually ends up cleaning the data.
Right. There was that incredible study on microbial growth dynamics mentioned in our notes.
I love that study. It was a brilliant real-world application because experimental biological data in a lab is always messy.
It's full of sensor noise and human measurement errors and just random temperature fluctuations.
Right, so the scientists took all this incredibly noisy raw data and they fed it straight into an autoencoder.
And because the noise is purely random, because it has no actual geometric structure to it.
The bottleneck just couldn't encode it. The random noise literally did not fit through the keyhole.
So when the decoder on the other side rebuilt the microbial growth curves, the noise was just entirely gone.
It flawlessly filtered out all the experimental error and revealed the pure underlying biological law. By aggressively compressing the reality, they actually found the truth.
That is such a profoundly powerful concept, this idea that lossy compression losing data is actually truth-finding.
It completely flips our intuition.
Yeah, normally we are taught that losing data is strictly a bad thing. More data is always better. But here, losing data is the only possible way to find the actual signal in the noise.
And this realization is what brings us right to the edge of what we comfortably know and pushes us straight into the active war zone of current scientific debate.
This is section 2, the active debate. Because if aggressive compression is precisely how artificial machines learn...
Is that how we learn? Is that what the phenomenon of intelligence actually is?
To dig into this, we absolutely have to talk about Naftali Tishby and his information bottleneck theory.
Tishby was an absolute giant in this specific field. He looked at modern deep learning models, and he asked a very fundamental, very simple question.
Why do they actually work?
Right. Why do these massive networks with billions of parameters actually work so well? Why don't they just lazily memorize the training data and then completely fail when you show them something new?
Which is the classic overfitting problem in statistics. If I just memorize the exact answers to the practice test, I'm going to bomb the real exam because the numbers will be slightly different.
Exactly. So Tishby applied rigorous information theory, which is the fundamental math of communication, directly to deep neural networks.
And he was tracking the flow of information, right?
He tracked exactly how much information the internal layers of the network retained about the raw input data versus how much information they retained about the final correct output label.
And he found that the learning process naturally splits into two very distinct phases.
Yes, and this was his truly revolutionary insight. He argued that at the very beginning of the training process, the network enters what he called the fitting phase.
Okay.
During this phase, the network is just greedily gobbling up information. It's aggressively memorizing the raw input. It has extremely high mutual information with the raw data.
So it's like a panicked student the night before a test, just highlighting absolutely every single word in the textbook.
Perfect analogy. But then after a while, something dramatic shifts internally. The network smoothly transitions into the compression phase.
And what happens then?
It starts actively shedding information. It starts deliberately forgetting the useless background of an image. It forgets the lighting conditions. It forgets the static noise.
It is minimizing its information about the raw input while maximizing its information about the actual target concept. So what you're saying is that true learning isn't just remembering things. True learning is actually the process of forgetting the right things.
That was quite literally Tishby's famous slogan. Learning is forgetting. You take a block of marble and you systematically carve away everything that is non-essential until only the pure concept remains.
That sounds so elegant. But of course, this is science, so nobody gets to declare a grand unified theory without a massive fight.
Oh no, it kicked off a huge debate. Researchers like Andrew Sachs and several others came along shortly after and essentially said, hold on, not so fast.
Right. Sachs published work showing that this beautiful, elegant compression phase doesn't actually always happen.
He demonstrated that especially with more modern network architectures, specifically ones using what we call ReLU activation functions.
ReLU rectified linear units. Those are basically just simple mathematical switches that completely turn off if the input value drops below 0, right?
That's a slightly simplified but perfectly accurate way to look at it. Sachs found that if you build a network with those switches, you can train networks that generalize perfectly well.
Meaning they pass the final exam.
Yes, they succeed in the real world, but they do it without ever explicitly dumping information in the measurable way that Tishby originally described.
So if the secret sauce isn't always explicit information compression, then what is it?
Well, this leads us directly to the alternative, which is the flat minima hypothesis.
Okay, let's unpack that.
Imagine the overall error rate of a neural network as a physical 3D landscape, a mountain range. You obviously want the network to eventually end up at the lowest possible elevation, right?
Right, the bottom of the deepest valley, because that means 0 errors?
Now, Tishby's framework sort of implies that to generalize, well, we need to find a very specific, mathematically perfect narrow valley.
A very precise solution.
But the flat minima view argues something entirely different. It says, no, we're actually looking for a very wide, very broad flat plateau of generally low error.
Okay, but why does physical flatness in this mathematical landscape actually matter for intelligence?
It is all about robustness, stability. If you are balancing on the incredibly sharp tip of a needle of perfect accuracy, and you take even one tiny step to the left.
Meaning the real-world data changes just slightly from what you trained on.
Exactly. You immediately fall off a massive cliff.
Yeah.
Your error rate skyrockets. You are wrong.
But if you are standing in the middle of a massive flat plateau, you can wander around freely. The real world can throw messy, noisy data at you, and you are still generally right.
Exactly. Your predictions remain stable. Now, having said that, I would argue, and I think Tishby's camp would heavily agree, that successfully finding a flat minimum is essentially just another sneaky form of compression.
How so?
Because if the landscape is flat, you are inherently describing your final solution with far fewer bits of absolute precision.
Oh, I see. You are saying the answer is roughly somewhere over in this general neighborhood rather than saying the answer is exactly at these precise GPS coordinates.
Precisely. It's an intentionally low-resolution strategy.
So even though the exact mechanics are fiercely debated, the overarching principle holds true. True intelligence fundamentally requires ignoring the hyperfine details to grasp the broader structural truth.
I think that is a very safe consensus, yes.
But we cannot possibly talk about the power of compression without addressing the dark side.
We have to talk about what gets lost.
Right, because if we literally start treating the messy human world as a mathematical manifold and we run algorithms to actively compress it, what happens to the people who are outliers?
This is what the field calls the interpretability trade-off, and the ethical implications here are just massive.
Because we are already aggressively using these exact techniques. We use complex nonlinear algorithms to embed thousands of dimensions of human data into simple, low-dimensional risk scores.
We use it for banking credit limits, for criminal recidivism prediction, for critical healthcare triaging.
And if you are an individual outlier, say you belong to a minority demographic whose historical data profile looks structurally different from the vast majority.
The cold, hard math of the compression algorithm is highly likely to treat your unique specific features as simple statistical noise.
Because it's trying to find the flat plateau for the majority.
Yes. It will actively smooth you out. It forces what we call a biased embedding.
So the actual topology of the generated map strictly dictates your real-world destiny.
If the compressed map mathematically distorts the distance between your specific data point and the concept of creditworthy, the AI is going to coldly deny your loan application.
And the most terrifying part is we can't even easily audit it to see why it made that choice, because the whole thing is an impenetrable black box.
The latent code inside the bottleneck isn't written in English. It's just a massive, unreadable string of floating point numbers.
Which is why the sources heavily emphasize the urgent need for fairness-aware embeddings.
Right. We have to somehow mathematically force the geometry of the compression to actively respect human social fairness, not just optimize for pure mathematical efficiency.
But from what I understand, that is a notoriously difficult mathematical problem to solve.
Extremely difficult.
Okay, so we have firmly established that our computers and artificial networks learn by aggressively compressing reality.
Mm-hmm.
But now I want to take a massive step back. I want to zoom way, way out, because this entire concept isn't just about silicon chips and code anymore.
No, it's about biology. It's about carbon. It's about us.
Which brings us to Section 3, Frontiers, where biology crashes head-on into thermodynamics.
And this is where the conversation gets truly wild.
The outline calls this section the information theoretic imperative, which honestly sounds like a supreme cosmic commandment.
It basically is a law of nature. So think about a single living biological cell, or just think about yourself.
Okay.
You are an incredibly highly organized physical structure. But the second law of thermodynamics absolutely hates you.
Because entropy desperately wants to break down that organization and turn me into a completely uniform puddle of warm, chaotic soup.
It does. Everything tends toward maximum disorder. So to actively resist that, to maintain your internal organization, to literally stay alive, you have to constantly harvest free energy from your environment.
Right, I have to eat.
But to successfully harvest energy in a constantly changing, unpredictable environment, you must be able to predict where that energy is going to be.
And concurrently, you have to accurately predict where the predators are going to be so you don't become their energy.
Exactly. So accurate prediction is not a luxury. It is a mandatory baseline survival trait.
But here is the massive evolutionary catch.
Your brain runs on about 20 watts of biological power.
Which is basically a dim light bulb.
Right. It is severely physically finite.
Right.
You cannot possibly process every single photon hitting your eye, every tiny air vibration hitting your ear, every stray molecule entering your nose.
We have a severe biological bandwidth limit.
A channel capacity problem. So to reliably predict the complex future using a physically limited biological brain, you are absolutely forced to heavily compress the past.
You have to rapidly strip the noisy environment down to its absolute bare causal bones.
The literature specifically talks about a concept called epistemic entropy.
Let's define that for the audience.
Epistemic entropy is essentially the mathematical measure of your total ignorance about what is going to happen next.
Okay.
The core argument here is that the entire process of living and surviving is just an eternal desperate war to actively minimize your personal epistemic entropy.
And what the sources suggest is that the absolute most energy-efficient biological way to accomplish that goal is to actually discover the fundamental laws of physics.
Wait, hold on. Break down that leap for me. How does simply trying to save biological energy somehow inevitably lead a species to discovering something like gravity?
Think about the pure mechanics of prediction. If I am a primitive hominid and I want to accurately predict exactly where a thrown rock is going to land, I could theoretically try to memorize the exact trajectory of every single physical rock I have ever seen thrown in my entire life.
Which would require a massive amount of neural memory.
And massive continuous energy consumption.
Yeah.
It is hopelessly inefficient.
Or alternatively, my brain can just abstract all those examples and learn one incredibly simple mathematical rule. Force equals mass times acceleration. F equals ma.
So if my brain can successfully compress all that raw visual data down into that one tiny equation, I can accurately predict the path of literally any rock I ever see with almost zero ongoing memory cost.
Exactly. So from this perspective, the fundamental laws of physics aren't some mystical truth sitting out in the void. They are literally just the ultimate optimal compression algorithm for raw sensory data.
So biological evolution actively pressured our primate brains to naturally become physicists, not because knowing the truth of the universe is inherently noble, but strictly because truth is incredibly calorie efficient.
It is a purely thermodynamic imperative.
And this is honestly the absolute biggest but of the entire exploration today.
I know exactly what's coming.
The cognitive scientist Donald Hoffman looks at all of this and says we are dead wrong.
Hoffman totally throws a massive wrench into this entire theoretical machine.
He agrees completely that our brains heavily compress data, but he aggressively disagrees with the idea that this compression leads us closer to the objective truth of reality.
Welcome to the interface theory of perception.
Tell us about Hoffman's evolutionary game theory simulations, because this is mind-blowing.
Hoffman ran millions of mathematical simulations, pitting entirely different theoretical types of organisms against each other in evolutionary combat.
Okay, so set up the board for us.
Let's say we have type A organisms. These organisms are perfectly evolved to perceive reality exactly as it structurally is. They see the raw, uncompressed quantum fields. They see the complex molecular structures. They see the pure truth.
Okay, and who are they competing against?
Type B organisms.
Yeah.
Type B organisms do not see the objective reality at all. They only see what Hoffman calls fitness payoffs.
Meaning what, exactly?
Meaning they don't look at a complex organic molecule. They just see a brightly colored symbol that strictly means edible or another symbol that means highly poisonous. They just see behavioral cues.
So they're completely blind to the true structural nature of the world.
It's entirely blind. So Hoffman runs these simulations for millions of generations. Who do you think universally wins the evolutionary arms race?
Type B, every single time.
Every single time. The organism that sees the objective truth always goes extinct. The theorem is literally called fitness beats truth.
Because perceiving the absolute truth is just too computationally expensive.
Way too expensive. If a tiger jumps out of the grass and your brain starts actively calculating the quantum spin states of the photons reflecting off its fur...
The tiger has already eaten you.
Exactly. You desperately need an interface that just flashes a giant warning sign that says, run away right now.
And this leads us to what he calls the desktop metaphor. And out of everything we read for this, I really think this is the most intellectually sticky idea in the whole stack.
It is a brilliant way to frame it. Think about the computer screen you use every day. Right now, you probably have a little blue trash can icon sitting in the corner of your desktop. Is that blue trash can true? If I open up your laptop case and look at the actual hard drive, is there a tiny plastic bin physically sitting inside there?
Obviously not. It's entirely a metaphor. It's just a convenient symbol representing a specific sector of magnetic memory on a disk that the operating system has marked as safe to overwrite.
And the digital file you drag into it, is it actually shaped like a little white piece of paper with a folded corner?
No, it's just a massive stream of invisible high and low electrical voltages.
So the icon you see is a complete lie.
It is an utter fabrication, but it is an incredibly useful lie. It aggressively hides the true staggering complexity of the physical hardware so that you can actually execute a task without needing a degree in electrical engineering.
Exactly. And Hoffman's radical argument is that space-time itself, the entire 3D physical space, we move through the linear time we experience the solid physical objects we interact with.
It's all just our biological desktop.
Space-time is entirely a data structure created by our specific evolutionary interface to facilitate human survival.
So the physical chair I'm sitting in right now, the table in front of me, the moon in the night sky, these are literally just 3D icons.
They are biologically generated symbols.
Right.
And importantly, a housefly is running a completely different evolutionary operating system. A bacterium is running a different OS. But none of us are ever seeing the actual physical hardware of the universe.
That is just genuinely dizzying to try to hold in your head. So you're saying we aren't compressing raw reality down to find the fundamental truth. We are actively compressing reality to completely hide the truth from ourselves.
We are hacking our own sensory feed. We are dynamically generating a user-friendly GUI for a universe that is fundamentally far too complex and alien for us to ever handle directly.
But hold on, if space-time itself is really just the GUI, just the software interface, what on earth is the hardware? What is the actual cosmic motherboard that is running this simulation?
And this is exactly where we have to finally turn to the theoretical physicist.
Yeah.
Specifically, we need to talk about the holographic principle.
Now, I know I've heard this specific term thrown around a lot in pop science media, and it's usually just used to vaguely imply we are living in the Matrix. But the actual physics behind it is so much stranger, isn't it?
It is exponentially weirder than the Matrix. And the entire theory actually originates from a massive crisis in physics known as the black hole information paradox.
Okay, set the scene for us. Why were the physicists panicking?
It started when Stephen Hawking mathematically proved something shocking. He discovered that black holes aren't completely black. They actually very slowly leak and radiate energy back out into space.
Hawking radiation.
Right. Which means that over unimaginable eons of time, a black hole will eventually evaporate entirely and just disappear.
Okay, that makes sense so far.
But here is the paradox. The foundational laws of quantum mechanics have an absolutely unbreakable rule. Quantum information cannot ever be fundamentally destroyed in the universe.
Right, like if I take a physical book and I burn it to ashes, in theory, If I could magically gather every single displaced molecule of smoke, every flake of ash, and every scattered photon of heat, I could mathematically reverse the process and reconstruct the exact text of the book.
Exactly. The local structure is heavily scrambled, but the fundamental information is never lost to the universe.
But if a black hole completely evaporates into nothing,
Then absolutely everything that ever fell into it is supposedly just gone forever, deleted from reality.
oh,
Yes. And this paradox triggered an absolute intellectual war in physics, primarily between Leonard Susskind and Stephen Hawking.
because if Hawking was right, then quantum mechanics was fundamentally broken.
Exactly. And the radical solution they eventually arrived at essentially revolves around the concept of surface area.
The Bekenstein bound.
Right. Jacob Bekenstein realized something profound. He showed that the absolute maximum mathematical entropy, the total limit of data or information that a black hole can physically hold, is strictly proportional to its two-dimensional surface area, not its three-dimensional interior volume.
That is incredibly bizarre. Because in normal daily life, if I have a cardboard box, the total amount of stuff I can fit inside, it obviously depends on the 3D volume inside the box.
Of course, but for a black hole, the ultimate data capacity limit is entirely dictated by the 2D surface of the event horizon, which heavily implies that all the physical 3D stuff supposedly inside the black hole is actually somehow perfectly encoded right on that flat 2D outer boundary shell.
Like a flat nutritional label on the outside of a soup can that mathematically contains the absolute reality of the soup itself.
Or more accurately, exactly like a hologram.
Right.
Because a physical hologram is just a perfectly flat 2D film. But when you shine a laser through it, an entire 3D image suddenly pops out into space. The 3D image is entirely a projection of the scrambled 2D data.
And then the physicist Juan Maldacena came along and just blew this entire concept up to encompass the entire universe, right?
Yes, with what is widely considered one of the most important papers in modern physics, the ADS-CFT correspondence.
Okay, walk us through that slowly, because the math here is heavy.
Maldacena discovered a mathematically perfect duality. On one side of the equation, you have a theoretical 3D universe that contains gravity, that is the ADS or anti-de Sitter space part.
Okay, a 3D universe with gravity. That sounds somewhat familiar to ours.
And on the exact opposite side of the equation, you have a completely flat 2D boundary surface that has absolutely zero gravity. It only contains quantum fields. That's the CFT or conformal field theory part.
And Maldacena mathematically proved that these two completely different theoretical worlds are actually the exact same thing.
He definitively proved they are mathematically 100% equivalent. They are an identical reality just described in two completely different geometric languages. You can literally translate any physical problem happening in the 3D gravity world directly into a problem in the flat 2D quantum world, solve it there, and seamlessly translate the exact answer back.
Which staggering implication basically means that the physical 3D world we feel like we live in right now with depth and gravity and volume might literally just be the emergent projection.
The bulk, as physicists call our 3D space, might just be a downstream emergent consequence of the true fundamental quantum entanglements interacting out on a completely flat, inaccessible boundary.
So let me just try to rapidly synthesize this entire stack before my head explodes.
Go for it.
Tishby and the computer scientists tell us that our cognitive brains are fundamentally just highly aggressive compression engines shedding data to find patterns.
Yeah.
Hoffman, the cognitive biologist, tells us that our daily physical perception is literally just an arbitrary evolutionary user interface perfectly designed to completely hide the true complex reality.
Okay.
And then Maldacena and the theoretical physicists tell us that the actual physical 3D universe itself might literally just be a projected holographic interface emerging from a lower dimensional flat surface.
You've got it. When you layer them all together, it overwhelmingly seems that this entire concept we casually call reality is actually just the final output of a massive multi-layered cosmic compression algorithm. We are literally living inside the bottleneck of the autoencoder.
Which honestly changes, well, it fundamentally changes absolutely everything. Which brings us to our final section, Section 4, Implications.
Right, because we really cannot just leave this entire discussion hanging as some kind of philosophical dorm room whoa dude moment. We have to explicitly ask what this actionable means for our near future.
And the immediate practical place this completely rewires our thinking is in artificial intelligence.
Specifically regarding a concept known as the machine scientist.
Because if intelligence is just advanced compression, then AI isn't just a fancy chatbot.
Not at all. There was a recent fascinating paper appropriately titled AI Physicist. The research team specifically built an artificial intelligence explicitly designed to do exactly what we've been discussing, aggressively compress complex raw data to mathematically isolate hidden underlying causal laws.
Okay.
They systematically fed this AI massive amounts of raw, disorganized data generated from a completely simulated mathematical universe. Things like the chaotic trajectories of bouncing balls and complex planetary orbital mechanics.
And to be clear, the AI wasn't just attempting to predictably guess where the balls would eventually bounce next, right?
No, that would just be standard deep learning. It did something much more profound. It utilized a technique called symbolic regression. It actively analyzed the raw noise, and it independently spit out actual clean algebraic equations.
That is wild.
It mathematically rediscovered Newton's fundamental laws of motion entirely on its own. It spontaneously rediscovered the fundamental conservation of energy. It looked at a wall of raw pixel data, and it successfully extracted the absolute underlying source code of that simulated reality.
So if Hoffman's interface theory is actually biologically correct, and our human brains are evolutionary trapped just mindlessly clicking on the simplified desktop icons of the universe, could a sufficiently advanced AI just look right past the interface entirely?
That is quite literally the trillion-dollar question of our era. Because our biological human brains are fundamentally hardwired for surviving on the ancestral savanna, we are permanently trapped inside our specific GUI because we biologically still need to forage for food and reproduce.
But an artificial intelligence inherently has absolutely none of that biological evolutionary baggage.
Right. An AI does not biologically need to fear being eaten by a tiger. It doesn't need to prioritize fitness payoffs over objective truth.
So theoretically, we could purposefully construct a superintelligence explicitly designed to completely ignore the evolutionary interface, an entity engineered specifically to directly read the raw quantum transistors of the actual universe.
We could leverage artificial intelligence to literally reverse engineer the grand simulation and to finally strip away the holographic projection and mathematically calculate the true intrinsic dimensionality of base reality itself.
I have to admit that is simultaneously the most intellectually exciting and genuinely existentially terrifying concept I have ever heard. We are essentially talking about intentionally peeling back the absolute final curtain of existence.
It is a profound threshold. But importantly, we also urgently need to focus on the immediate societal implications of applying this raw compression mindset to ourselves right now. We briefly touched on the inherent algorithmic bias earlier, but honestly, the danger goes so much deeper than just loan approvals.
You were talking about applying the strict logic of manifold learning directly to complex human society.
Exactly. Because we are currently in the rapid process of digitizing absolutely all of humanity. We are aggressively converting incredibly complex, messy, nuanced human lives into simplified rows of data vectors.
And then we're mindlessly running massive autoencoders to forcefully compress those human vectors just to make administrative decisions. Who gets hired for a job, who is granted early parole, who gets shown a specific political ad. And as we thoroughly established earlier, the very nature of compression mathematically mandates profound loss.
You cannot compress without discarding data. And when you algorithmically compress an entire living person down into a simple mathematical risk score, you aggressively strip away their essential humanity. You mathematically erase all their vital context and nuance.
We are essentially engineering a society structured entirely around interacting with highly degraded, lossy JPEGs of human beings.
We are no longer interacting with the full resolution reality of each other. We're interacting strictly with the compressed artificial avatars that the algorithms generate.
Which is a remarkably bleak trajectory if we don't actively correct course.
But to pull us out of that slight tailspin, there's also a profoundly beautiful philosophical shift buried right at the bottom of all this source material.
Oh, yes. The profound implications for the hard problem of consciousness. Because if Hoffman's interface theory is actually correct, and this space-time interface is entirely generated by consciousness,
this sparks a massive, modern return to philosophical idealism. If space-time itself is ultimately just a convenient, localized data structure, then space-time cannot possibly be the fundamental building block of the universe.
So what on earth is?
Hoffman passionately argues for a framework he calls conscious realism. The radical proposition that the actual fundamental structural constituents of the universe are simply networked conscious agents.
And spacetime itself is really just the highly compressed dashboard language that these conscious agents spontaneously use to interact with each other.
Exactly. It completely flips the standard materialistic scientific worldview entirely upside down.
So we fundamentally are not just random inert bits of cosmic matter that eventually somehow evolved internal consciousness.
No, we are infinite consciousness actively imagining localized bits of matter.
And honestly, that profoundly suggests that the entire underlying goal of biological life, the ultimate purpose of this whole grand physical experiment, isn't just to mindlessly gather and hoard more raw information.
Right. It's definitely not about endlessly hoarding terabytes of noisy data on a hard drive.
It's strictly about achieving better, much more elegant compression, which, when you think about it, is really just another word for wisdom.
That is a genuinely beautiful way to frame it. True wisdom is simply high-efficiency mental compression. It's the incredibly rare cognitive ability to observe an overwhelmingly complex, noisy, chaotic situation and instantly, cleanly extract the single, simple, underlying truth.
That is quite possibly the most profound definition of wisdom I've ever heard. The truly wise person in the room isn't necessarily the one who memorized the most random facts. The wise person is just the one who naturally possesses the absolute best internal encoder.
Precisely. They see the signal clearly through all the noise.
Before we go today, I want to leave everyone listening with one final, very specific thought to just mull over. We have spent this entire time talking about how these autoencoder networks mathematically optimize for what is called reconstruction error.
Right. They continuously tweak their internal parameters to ensure the final output picture remains as absolutely clear as possible.
So if we assume the entire universe is essentially operating as one massive dynamic compression algorithm, what exactly is it optimizing for? What is the actual ultimate loss function of reality itself?
Is it simply optimizing for maximal complexity? Is it driving toward infinite novelty? Or is the universe fundamentally just optimizing for self-recognition?
That is absolutely a question for another entire exploration.
Indeed it is.
Before we wrap up, thank you to all our partners, sponsors, and scholars who made this podcast and the research possible. We're truly grateful for your support.
And to our listeners, thank you for being part of this journey with us. We hope you enjoyed today's discussion. If you did, be sure to subscribe and support us on Patreon. And of course, you can write to us in comments if a specific topic needed to be covered, which help us all to grow.
Until next time, stay curious, keep learning, and let the search for wisdom guide you forward. Have a great day.